Hello, let's get to the topic of Lie theory. First, the notion of Lie groups comes in the Lie theory. A Lie group can be defined as the intersection of two fundamental fields of mathematics, algebra and geometry. A Lie group itself is first of all a group. Secondly, it can be thought of as a smooth manifold which has a specific kind of geometric object. For example, circle and a sphere are examples of two smooth manifolds. A Lie group of symmetry should have the continuous symmetries. For example, a circle has a continuous symmetry, so it is a Lie group. But for a hexagon, we cannot have the continuous symmetry. It is discrete, so we cannot consider hexagonal groups as a Lie group. The Lie theory was originated and studied by mathematician Sophus Lie. Initially, we used change of variables to solve the equations, but later we observed that the equations are symmetric, so we exploited this property and used them in the Lie theory to solve them. So here we get the concept of smooth curve. The smooth curve is that which is continuous and differentiable as well. To analyze the Lie groups, we introduce the concept of Lie algebra, which is a flat space. So, in the earlier sections, we talked more about symmetry. So, what symmetry really means. Suppose an object in the space and we rotate that object by some small amount or any arbitrary amount theta, and the properties of it remain same, or it is the changes are unobservable. Considering a circle and rotate it about origin with some angle theta, and the new figure formed is exactly same as the previous one. But considering an hexagon, when we rotate this by some angle not equal to integral multiple of pi by 3, we get some figure like this. So we can clearly see that these two figures are not congruent and the difference of them are observable. So the case of hexagon is an example of a finite symmetry, and the case of a circle is example of a continuous symmetry group.
So now we will look at when will it be symmetric for a hexagon. We know that hexagon is symmetric. It has six sides, so each internal angle is 60 degree. So if we rotate the hexagon with 60 degree or pi by 3, we will get a symmetric figure. So if the symmetricity criteria for a hexagon is the rotation with angle integral multiple of pi by 3.
As we had the notion of Lie groups, we can now further divide it into subparts. We will take the example of a mapping going from n-dimensional space to n-dimensionless, that is r power n to r power n. If this mapping is preserving both volume and orientation at the same time, then this type of mappings are called linear groups. And if the mapping preserves distance, then this type of mapping is called orthogonal groups. And we can have many more is like that.
So let's get to the topic of Lie algebra. It is a vector space together with a non-associative multiplication which you call as a Lie bracket. and this is represented as square bracket x comma y.
Now we will discuss about the properties of Lie algebra. First comes is bilinearity, which says ax plus by comma z is equal to a times x comma z plus b times y comma z. Also, z comma ax plus by is equal to a times x plus b times z comma y, where a and b are in F, and this holds for all x comma y comma z in G. Second property of the Lie algebra we'll talk about is alternativity, which says Lie bracket of x with x itself is 0 for all x belongs to G. Now third and very important property is Jacobi identity, which says x with y comma z plus z with x comma y plus y with z comma x sums up to 0 for all x and y and z belonging to G itself. In the earlier property, we use bilinearity to expand the bracket x plus y with x plus y. Also, we use alternativity to show x with y plus y with x equal to 0 for all x and y belonging to G. And at last, we have another property, anti-commutativity, which says Lie bracket of x with y is negative times of Lie bracket of y with x for all x and y belonging to Z.
Okay, so hello everyone. We are going to talk about integer solutions to a particular equation which is quite famous, x cube plus y cube equal to z cube. Okay, so well, you have these rational points on curves, right? So, well, I can write this equation as x cube by z cube plus y cube by z cube is equal to 1. And as we all know that p by q is a rational number, the way of representing a rational number is obviously p by q, where q is not equal to 0. So yeah, so when you write this equation in another form, it can be written as, you know, x by z the whole cube plus y by z the whole cube equal to 1, which is equivalent to saying u cube plus v cube is equal to 1, where u is x by z, v is equal to y by z, and u and v are rational numbers. So as you can see, these are rational points on a curve. And how do you get the solutions to these? Okay, so now as we all saw, u cube plus v cube is equal to 1, and we wrote this as, we had x cube plus y cube is equal to z cube. And why have we written this? Okay, so the answer is this. First of all, it reduces the number of variables by 1. There you had x, y, z. Now you have u and v alone. Also, it helps us to analyze the situation in a better way. Now we'll see how this helps. But first, these are the two motivations behind writing this equation in this way. Now, as we look forward, this is also called as a polynomial curve. a polynomial curve of two variables where u and v are the variables of the polynomial curve. As you can see, this is what we try to aim to. We try to find how many rational points on this curve there exists and how many rational points can exist on this curve. So for that, before they go over there, we'll introduce the notion of a genus. What is a genus actually? To help the situation to analyze this better. So yeah, so to help analyze the situation better, what is a genus? In very abstract terms, genus is the number of holes in a curve. Now, what do you mean by holes? Well, we'll get to it in a short while. Number of holes in a curve. Can you imagine it this way? Well, the first example that I'm going to give you right now is, well, genus has a particular order, you can say. And first of all, we're going to discuss the number of holes in a curve. Right. So there you go. First of all, we take the example of, what do you say, a sphere? Yeah, let's go on with it. So a sphere, or maybe you can say a disk. Can you imagine it? Well, does it have any holes inside its, structure? Does it? No, it doesn't. It covers the entire surface area in this scope of a disk, and in the case of a sphere, it does actually cover the entire volume. So no holes. Genus is zero. Fine. So yeah, it's pretty abstract actually. So if you notice, it's not much of a difficult thing. Secondly, let's take an example of a torus, somewhat like this. Okay, so it has a one hole in it. So this has a genus of 1. Well, genus is the number of holes in a curve. So very abstract terms here right now, but that's how we're going to proceed through with this. So an interesting example that I want to give you forward now is that of a coffee mug. Well, I'm going to draw a coffee mug right now, and as you can see, its handle. Well, this handle is like it has a genus of 1 because it has one hole in it, right? So this is one interesting example that comes to our mind. Yes, handle has a genus 1. Okay, so how do you relate a genus of a curve to the rational points solution? Now that is what our topic of intention is. That is what we are going to discuss right now. That is important to discuss because this concept will help us realize how easy it is to analyze the situation. Now, as we see, well, I have an idea right now. How do I go about this? Well, nice idea that can be maybe, yeah, consider consider this curve, x squared plus y square is equal to z square, which can also be written as u square plus v square is equal to 1, which essentially I divided the equation by z square. As you can see, I'm not going to show it again as I did it previously. Also, this equation that I have just written out here, well, it has infinitely many, first of all, let me write this. It's my idea, right? So, yeah, it's an idea, not a tree or something. It's a bulb, actually. So, yeah, infinitely many Pythagorean triplets, as I was going to mention. Uh, yeah, infinitely many Pythagorean triplets that are not multiples of each other. Or you can say that, if this is the case, well, let me just complete it first. Infinitely many Pythagorean triplets that are not multiples of each other. So after this, as I conclude, well, yeah. So this concludes me to believe that there are infinitely many solutions to this curve, or infinitely many solutions to u and v. Yeah, let me just write it down. It has many, or you can say infinite rational points. Yeah, u and v. Okay. Okay. So how, well, we also know that the genus of this curve, well, let me write out. What is the genus of this curve? The genus, as is found out, is turns to be 0. So it's a startling assumption, startling thing. So yeah, continuing from the previous slide, how is this genus related? So we found out that genus was 0 for a curve. It meant that either you had infinitely many points, or let me just pen it down right now, infinitely many, or maybe you can also have no solutions to this, right? You can either have infinitely many solutions to u and v, or you can have no solutions, no rational solutions, I mean here, be very precise over here. Now, one thing we learned, one thing we notice, and one thing we need to know is that the genus 1 is an elliptic curve. Okay, so as we see, well, elliptic curve contains infinitely many, but but it has a restricted structure. It contains infinitely many rational points, but it has a very restricted structure. In that it is saying that how do I write this? Well, it basically means that the subgroup of rational points on elliptic curves was finitely generating an infinite structure. Okay, yeah, subgroup of rational points on an infinite curve randomly generates this. Now we turn our heads to models conjecture. As we discuss the terms of genus, what about genus 2? Have you ever seen of it? Like, have you ever thought about it? Or have you ever guessed about it? Well, what model said here is that, and it's a very good conjecture. In mathematics, conjectures turned out to be, pretty well proved wrong. But well, let us see what happened to this. He said that a curve of genus of at least two in number could take, or you can say it contains only finitely many points, finitely many rational points. A startling result. It was it was thought to be a conjecture. That is why its name is a conjecture. you know this can have many implications, does it not? Well, it is remarkable. First of all, let me just write it down, because why consider uh say a genus of curve of at least two, right? So x to the power n plus y to the power n is equal to z to the power n. Well, this is the Fermat's equation. If you remember, this is a very, very popular equation. And how, well, if this conjecture was true, it meant that this particular equation had only finitely many points. Now, since this was remarkable, well, many still, do not believe it, to be very honest. Well, I was conducting this research about it and got to know about it. So, but then Faltings came over, and Faltings, well, he proved it. Now it turned out to be, surprising, because most of these conjectures were not proved earlier on, and Faltings came and Faltings proved it. So now we got a very, very nice, remarkable entry into the world of Diophantine equations. Well, there is a limitation though that I'm going to mention. It is ineffective. Now this limitation, being ineffective, means that models conjecture, well, for some points it may be defined, for some it may not be, but the overall encompassing of the structure is not done. But that's what models conjecture is, and that's what ends this theorem. Well, thank you so much, and have a nice day.
Louie Chebyshev. He was one of the greatest mathematicians of his time. He was mostly known for his work on prime numbers, and he even came close on proving prime number theorem. He was born on May 4th, 1821, in a military family. He studied at University of Moscow and taught at St. Petersburg. He died on December 8, 1894. He was born in village of Okotova in district of Provetsk, Russia. His parents were Ivanova and Pavlovich. His disability prevented his playing many children games, and he devoted himself instead to mathematics. He never married and lived alone in a large house with 10 rooms. In his early days, Pafnati was educated at home by his mother and a cousin. His cousin Evdotita became very important for him, as she taught him excellent French and arithmetics. In 1832, the family moved to Moscow, and Pafnati received private tuitions by the mathematician P. N. Progliski. Later, in 1837, Chebyshev started to study mathematics at the University of Moscow. The most important professor for him at Moscow University were Nikolia Efimovich and Nikolia Dmitrovich, who taught probability there. This is the picture of University of Moscow. In 1841, Chebyshev was awarded silver medal for his work on calculation of roots of equation, which he had finished in 1838. In this, Chebyshev derived an approximation algorithm for the solution of algebraic equations of nth degree based on Newton's method. Between 1843 and 1847, Chebyshev worked on a thesis which he finally submitted in St. Petersburg to get a position there. It was entitled on integrity by means of logarithms. In 1842, Chebyshev submitted a paper in French language to Joseph Liouville, which he published in his journal of 1843. Chebyshev's second paper about probability was in the same language and was published in Searle's journal of 1847. In 1847, he became professor at University of St. Petersburg. This is one of the pictures of the university. Jointly with Viktor Yakovlevich, he published a complete edition of Leonhard Euler's book about 99 numbers, which appeared in 2 volumes in 1849. In 1850, Chebyshev became extraordinary professor at St. Petersburg. Every year, Chebyshev undertook travels to conferences in Western Europe and to different academies. In 1882, Chebyshev retired from his position at the University of St. Petersburg. This is one of the picture of Viktor. Chebyshev received an award of the Russian Academy of Science for his book Theoria Severnae about the theory of numbers. The crater Chebyshev on the moon bears his name. He is often considered as the father of Russian mathematics. Chebyshev became a member of many royal societies throughout the world, like Royal Society of London.
Let's see the application of mathematics. Let's say I have a distribution of probability like this, and I have 3 lines, left, right, and center, with the center being the mean, and the left and right being 1 standard deviation away from the mean. Well, how do I find the data between these lines? Similarly, I have a left mean skewed bar graph, which is a bar graph with its mean to its left instead of the center. Let's just draw this. Yeah, with its mean here, and I have 2 points marked -1 and 1, which mean that there are some standard deviation away from the mean. Well, how do I find the data between these 2 points? Lucky for us, the Chebyshev's theorem comes to a head. It states that the proportion of any distribution lying between k standard deviations, let's write it, is directly proportional to 1 minus 1 upon k square, where k is more than 1. This is a very important equation in mathematics. Let's take a case where k equal to 2. So our formula becomes 1 minus 1 upon 4, which gives us 3/4, which implies that 75% of the data is within 2 standard deviations of the mean. And plugging k equal to 3, we get that almost 90% of the data is between 3 standard deviations of the mean. Let's see an example of Chebyshev's theorem. Let's say there's a maths test with the average being 84 and the standard deviation being 4. And let's say our aim is to find the percentage of tests which have score less than equal to, okay, first say more than equal to 72, and let's say less than equal to 96. Yeah. So the approach to the solution is we draw a number line with 84 in the middle, somewhere, yeah, right here, and we approach from 84 till 72, taking steps of standard deviations. So we go from 84 to 80, that is one standard deviation. Then from 80 to 76, that is another standard deviation. Yeah, and yeah, and then from 76 till 72, that is another standard deviation. So 3 standard deviations this way, and then we go from 84 to 96. So we go from 84 to 88, that is one standard deviation, and then from 88 to 92, that is another standard deviation, and last we go from 92 to 96, that is another standard deviation. So we have gone 3 standard deviations either way of the mean. So for a formula k equal to 3 and plugging in the Chebyshev theorem, we get that 1 minus 1 upon k square gives us 1 minus 1 by 9, which gives us almost 90% of the test score lie between 3 standard deviations of the average. Now let's study about another important contribution from Chebyshev called the Chebyshev's inequality, which states that for a random variable x and its mean being, let's say, mu, and its variance being, let's say, sigma square, yeah, and for a variable k which is more than 0, we have the probability of mod x minus mu being more than equal to k. This probability is less than equal to sigma square by k square, with the constraint that k should be more than 1, because if k will be 0 then this probability wouldn't make sense. Yeah, I think this should be 1, my mistake. Now I must emphasize on the specialty of this inequality. This can be applied to any distribution of probability, and I emphasize on any. The only constraint on the probability distribution should be that one should know the mean and the variance of the distribution, and then this inequality can be applied to it without no hesitation. Now let's see an example of Chebyshev's inequality. Let us take a random variable x, which denotes the number of items produced weekly in a factory. Let me write it down. Yeah. With the variance, that is sigma square, as 25, and let the mean be 50. Now we have to find the probability that the items produced next week are either more than 60 or less than 40. We can represent this by a Chebyshev inequality by taking k as 10. So we can write it as p mod x minus 50 more than or equal to 10. And since we know that k equal to 10, we can directly plug in the variables into the formula, that is sigma square by k square, where we are given the value of sigma square as 25 here. So we can directly say the probability will be equal to 25 by 10 square, which comes out to be 25 by 100, which is 1 by 4.